go ahead and record. So we're doing section 6.5 today. We will do 6.6 on Monday, and then do review day, and then your test will be the end of the week. So we are going to graph the other 4 trig functions today. Okay, first one is the tangent. The tangent and all of the other ones all have asymptotes. There are asymptotes on tangent, cotangent, secant, and cosecant. They all have tangents. Okay, and the they all have vertical asymptotes. I mean, so the tangent of x has a vertical asymptote every pi starting at pi over 2. Remember, the tangent is the sine over the cosine. So you're going to have an asymptote wherever the cosine is equal to 0. Right? Because if it's sine over cosine, it's undefined when the cosine is 0. That's why you have asymptotes, where the cosine of x is equal to 0. That's why you have asymptotes there, because there are places where it won't exist, because you're not allowed to divide by 0. The world will explode. Well, maybe not. It's all fun and games until somebody divides by 0. Okay. Your domain and range. Okay. Your domain, your x inputs, are everything except for where the cosine is 0. So every odd pi over 2 value, 1 pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, 9 pi over 2, any odd pi over 2 value, including negative ones, negative pi over 2, negative 3 pi over 2, negative 5 pi over 2, negative 7 pi over 2, any odd pi over 2 value, it's undefined, it has an asymptote, those numbers are not in the domain, because your cosine for those values is 0, you're not allowed to divide by 0. Your asymptotes are where your domain does not exist. Okay? Your range is everything. You will get every possible y value out of it. So it goes forever up and forever down. Okay? Now the period on sine and cosine are 2 pi. The period on tangent is pi. It's half of that distance. And this is because it's sine over cosine, and the tangent repeats itself as you go around. If you think about the unit circle, the top half you go around, and then those numbers repeat as you go around the other way, because you have on your first set of inputs for sine and cosine going around are both positive, so your tangent's positive, and then your cosine changes to negative, and so you have a negative tangent, and then both of them are positive again, so you have a positive tangent, and then your sine's negative, so you have a negative tangent as you're going around. And it does, the top half, and then it repeats on the bottom, and then it goes on the top, and then it repeats on the bottom. So your tangent, the tangent values for the top half are the exact same ones as you continue around on the bottom half. That's why it recycles every pi, not every 2 pi, not as you go around. It's the top half of the circle, and it repeats itself over the bottom half of the circle. It's not a reflection, it's a repeated one. So that's why it's every pi, not every 2 pi. Okay? So the tangent is this is going to be the hardest one to graph straight up. What you really want to do is you want to look at where are my zeros and where are my asymptotes, because that's the easiest thing to find on the tangent. Where are my zeros? Where are my asymptotes? It is 0 wherever the sine is 0. So let's go ahead and put on our lines here. So it's going to be every pi over 2, pi over 2, pi, 3 pi over 2, and I'll go up to 2 pi here. And for snorts and giggles, I'm going to go backwards. Negative pi over 2, negative pi, negative 3 pi over 2, and negative 2 pi. So I'm going to go in both directions on this one and give several cycles. Okay, I'm going to give you several cycles of the graph. Even though most of the time you're going to need to give me 2 on tangent, I'm going to give you several cycles. Okay? So, when I graph this out, my key is, what I said is, where is it 0? Where are my asymptotes? Those are the 2 most important things when you're graphing the tangents. Your zeros happen where the sine is 0. The sine is 0 at 0 and pi and 2 pi, and working backwards, negative pi, negative 2 pi. Your sines are 0 out this way, right? 0, pi, 2 pi, 3 pi, 4 pi, 5 pi, going backwards, 0, negative pi, negative 2 pi. Same thing. On your integer values of pi, your sign is negative. Those are your zeros. Where are my asymptotes? Where the cosine is 0? Cosine is 0 at pi over 2 and 3 pi over 2 and 5 pi over 2 and 7 pi over 2. Every odd pi over 2. So on the pi over 2s, I have asymptotes because the cosine is 0 at those places. Okay? Zeros and asymptotes are the most important, are where your starting point is. Okay? Now, it does this John Travolta disco thing. It looks very similar to cubics. It's not, but it looks similar to a cubic equation. And here's how it works. It comes up, goes through, and goes up. Comes up from below, goes through the 0, goes up. Comes up from below, goes through the 0 and up. Comes up from below, goes through the 0 and up. So as I'm going from left to right, it goes from positive to negative. Okay? Same thing here on this one. That's a lousy looking asymptote. Okay? That's what the tangent looks like. It's not a pretty graph, but that's what it looks like. It's got this disco thing going on. Every pi over 2, between the pi over 2s, it looks like this. It crosses at the pi's, at pi over 2s, you have asymptotes. Okay? Questions? Tangent and cotangent are probably the most difficult ones to graph. Get sine and cosine down. The rest of them are easy. This one kind of works off of it. And remember, everything that you're doing focuses on sine and cosine. If you know your sine and cosine values, it makes it easier to do everything else. Where are my asymptotes at? Where cosine is 0. Where are my zeros at? Where sine is equal to 0. If you know your sine and cosine values, it's easy to graph. Okay. The cosecant of x. Okay. Now the cosecant of x, the whole key to graphing the cosecant of x is remembering that the cosecant of x is 1 over the sine of x. Okay, the cosecant is 1 over the sine. So my asymptotes are where the sine is equal to 0. I do have asymptotes. Wherever the sine is 0, I have an asymptote. Okay? Your domain is everywhere I don't have an asymptote. Same thing as the tangent. Your range is where it gets goofy. Your range is where it gets goofy. Okay? The sine, the range for the sine is between 1 and negative 1. Okay? The cosecant is 1 over those values. So when I have the sine as 1, my cosecant is also 1. As the sine decreases in value, I have the inverse of that. So 1 over a decreasing value is actually an increasing value, right? If I go from 1 to 3/4, 1 over 3/4 that is actually 4/3, right? It goes up. It starts going up. The smaller my denominator gets, I should say, the closer my denominator gets to 0, the closer the fraction goes towards infinity. That's what's happening here. So my range goes from negative infinity to 1 and 1 to infinity. And when you see the graph, you'll understand what I'm talking about. So I have up here already, and it's down on your sheet, a sine curve. Because when you go to graph the cosecant, if you sketch the sine, the drawing the cosecant is very, very easy. So I have a sine curve already in here. I'm going to put in asymptotes. My asymptotes go where my sine is 0. So anywhere my sine is 0, I have an asymptote. Okay. And by the way, the period for this is the same period as it is for the sine. Okay, period works the same on cosecant as it does for the sine. And then I want to graph the equation. Now, when the sine is 1, 1 over 1 is 1, right? As this value gets down smaller, 1 over that value gets larger. So here's what happens to the graph. It actually looks like that. That's what the cosecant looks like. And if I do it from this way, it goes up from the negative and goes down that way. It comes down, and it goes up, and it repeats itself over and over again, just like the sine does. Okay. So the solid line that I have there, that is my cosecant. And then what it does, what it looks like is it looks like a bunch of parabolas, okay, that come down and touch the top of the sine curve or come up and touch the bottom of the sine curve. That's what it looks like when you graph it out. You can see why the domain is from 1 to infinity, because what's the smallest possible value the cosecant can be? The smallest value of the cosecant is 1, right? Because the smallest value of 1 over number is when you have the largest value in the denominator. The largest value in the denominator will give you the smallest value of the inverse. So when I have 1 in my denominator, I have 1 for the whole thing. That's the smallest possible value it'll be. And then it works in the exact reverse. These are inverse functions. Inverse of numbers, inverses of declining numbers, grow. Inverses of growing numbers, decline. That's how it works. Okay. So the cosecant does not exist between 1 and -1. But it exists everywhere outside of 1 and -1. Okay? Questions on that? Okay. When you go to draw a cosecant equation, sketch in the sine and then do the loops above and below. That's really honestly what you need to do. The secant is 1 over the cosine of x. So this works the same way. Only instead of instead of the zeros from the sine, we have the zeros from the cosine. Instead of the 1s from the cosine, we have the sine, we have the 1s from the cosine. Other than that, it works exactly the same way. Remember, the sine and cosine are the same graphs, just phase shifted. The secant and the cosecant are the same thing. They're the same graphs, just phase shifted over, because they operate exactly the same way. Our asymptotes are nearly identical. Once again, they're shifted over, though. Instead of being where the sine is 0, it's where the cosine is 0. Wherever the cosine is 0, I have an asymptote. Okay. So the first thing I want to do is I want to draw my cosine curve, and then I want to put in my asymptotes. And then the same thing happens with these that happened with the sine curve. For the secant, goes up and touches and then comes back down. Comes down and touches and goes back up. Comes up and touches and goes back down. And then on this one here, we have a half one here and a half one there because that's what fits in our graph. And once again, the period is the same. It's 2 pi. Period of a cosine is 2 pi. The period of the secant is 2 pi as well. Okay? Not too difficult to do, really. If you can graph a sine, you can graph. If you can graph a sine, you can graph a cosecant. If you can graph a cosine, you can graph the cosecant. Really, I do think these are actually of the odd ones. These are the easier ones to do. Tangent and cotangent are where things get kind of hairy. And you just have to know what they look like, and you have to memorize which direction they go. And I have to stop to think when I come back to this after having not done it for several years. Okay. Questions on the secant? The cotangent. Okay, the cotangent, remember, is the cosine of x over the sine of x. It's the inverse of the tangent. So I wouldn't really go by where the tangent is 0. I would go by where the sine of x is 0. You're going to have asymptotes wherever the sine is 0. If you know your sine and cosine values, you can find everything else. That's the hardest thing. If you can get the sine and cosines memorized, or figure out, or not necessarily, not just memorize, figure out how to figure them out, because you know how the circle works. If you can find out what those values are, that can spit everything else out for you. So you want to, you have asymptotes here wherever the sine of x is 0, and the sine of x is 0 at 0 and pi and 2 pi and 3 pi and 4 pi and 5 pi, every pi value, right? Every integer of pi, both negative and positive. Okay, and that would be the same thing. So the cotangent has asymptotes at every value of every integer value of pi. Okay, and on here, this has got the tangent curve. So the tangent curve, the tangent's 0 at all those places. So this would be negative pi here. This is negative 2 pi here. This is 0. This is pi. That's 2 pi. So the graph that's on there is the tangent pi. So every one of those are my asymptotes on this one. So I have an asymptote here. I have an asymptote there. I have an asymptote here. I have an asymptote here. I have an asymptote here. Everywhere the sine is 0, I have an asymptote. Where are my zeros at? My zeros are where the cosine of x is equal to 0. So those are my asymptotes. That's where it crosses the x-axis. That's the other place I want to look at, which happens to be everywhere in between. All the pi over 2s, all the odd pi over 2, 1 pi over 2, 3 pi over 2, 5 pi over 2, going negative, negative pi over 2, negative 3 pi over 2, negative 5 pi over 2. So all of these, my pi over 2s, are where it crosses the x-axis. Yes?
Like pi over 2, wouldn't it be undefined there as well?
No. Pi over 2, it's because why is it infinite? It goes up forever because the denominator is getting really small as the numerator is getting larger. Okay, that's what's happening here. So as I, for example, approach, so as it approaches there, but what's happening is if you flip that over, then the denominator is getting really small as the numerator. Sorry, the numerator is getting really small as the denominator is getting really large, which means it's approaching 0, not approaching infinity. So the inverse of infinity, 1 over infinity, is 0. 1 over 0 would be infinity. It's headed towards infinity. It's kind of where you're at, which is a prelude to limits next year. Okay. So yeah, and I just go by where sine and cosine are 0. Wherever it's undefined, I have an asymptote. Wherever the numerator is 0 and the denominator is not, I have 0. Makes it easier. Now, the thing about the cotangent is instead of rising as I go from left to right like the tangent does, it declines as I go left to right. Because remember, it's the inverse of this. So wherever the tangent would be negative, it's it's the inverse. So it's kind of goofy, but what it does instead of rising, it drops. So I'm doing the disco thing the other direction. And that's the cotangent. Like I said, cotangent and tangent are probably the two most difficult ones to do. Honestly, they're the ones I have to take a minute and stop and think about and kind of plan it out a little bit more. Okay? Any questions? Okay. Yes. Yes.
When you're graphing this, you don't have to like put a dotted lines on the asymptote.
It helps considerably to do them. It really helps considerably to put the asymptotes in. I can't draw a good one without the asymptotes. I put my asymptotes, I put in my zeros, and then from there, once you get the asymptotes and zeros in, it's okay, tangent climbs, cotangent goes down. And I just go between the asymptotes, either going up or going down as appropriate. That's literally how I do it. Figure out my asymptotes and my zeros. That's the easiest way. Okay, so, yeah. This is where things get a little tricky, but they're not bad. Okay? So I have the 2 times the tangent of 1/2 x minus 1. The 2 in front does my amplitude, is what we were doing with sine and cosine. On tangent and cotangent, it really doesn't do much. It's kind of like a stretch with a parabola. It just makes it grow faster. You can't really draw that 2 in there. It's not like it moves it to, it's not like it takes and stretches the top and bottom like sine and cosine does. With tangent and cotangent, it goes on forever anyways. It just goes twice as fast. That's all it does. It just makes it grow faster. Your asymptotes are still in the same place, okay, based upon the period. Okay, so this is where it gets a little tricky. That 1/2 is actually what makes it. The 1/2 is what makes this one the hard one. That's what makes it the hard one. Okay, 1/2 x is what makes it difficult. So I need to do a period adjustment. What's the normal period? What was the period for sine and cosine? 2 pi. What's the period for tangent? Pi. There you go. So instead of doing this, I now have pi over w is what gives me my period. So instead of pi, it is now pi over 1/2, which is my period is 2 pi. So instead of getting a cycle every pi, I now get a cycle every 2 pi. Or actually, it's basically 2 cycles in every hour. I get a cycle every 2 pi. Okay. And the -1 is a vertical shift. So basically what that says, instead of my zeros being on the x-axis, my zeros are now going to be on the line -1. So my zeros move down 1. So all my zeros are going to be on there. All my asymptotes are going to be on the, are still going to be on the same place. Okay. So zeros and asymptotes. I have a 0 wherever the sign is 0. Okay. So if I look at this as being the sine of x, sine of 1/2 x, I want to know where is that 0. Well, it's still at 0, right? So I put in 0 for x, what do I get? I still get 0, right? So at 0, I still have a 0, which isn't crossing the x-axis. It's now at the -1 point, right? Where is my next 0 going to the right? Where would it normally be without the 1/2? It would be at pi, right? Because we put 0, 0 again at pi. But if I put pi in there, that's actually at 1/2 pi. So what do I need to do? I need to put in 2 pi. So if I put 2 pi in here, if I put 2 pi in there, it's actually the sine of what? The sine of pi. 1/2 times 2 pi is pi, right? So it's not the sine of 2 pi, it's the sine of pi, which means if I do this and have that be pi, and have this one be 2 pi, there's a 0 there. And if I work backwards and have negative pi here, negative 2 pi here, there's another 0. Does that make sense? Because my cycle would be twice as much. It would be zeros. Instead of zeros every pi, it would be 0 every 2 pi. Okay? Now here's a really cool thing. I said the 2 most important things are my zeros and my asymptotes. I found my zeros. My asymptotes are extremely easy to find when I find my zeros. They're halfway in between. If I know where my zeros are, my asymptotes are halfway between my zeros. Every single time. And and vice versa, if I know where all my asymptotes are, I know where my zeros are. My zeros are halfway between my asymptotes. So if I know my zeros, I know my asymptotes. And I know my asymptote from a hole in the ground. There's an asymptote there. There's an asymptote there. There's an asymptote there. And there's an asymptote there. Halfway between my zeros are my asymptotes. Halfway between my asymptotes are my zeros. And then it's a tangent, right? So what does it do? It goes up. Remember, you're passing through the 0 point on the -1 line. Yes. That is extremely difficult to do by hand. So you really don't worry about the 2 in front, because it's just going a little faster. It's very hard to do because it's very hard to graph them well by hand to be more accurate than the points that I have. Those are the points you need for accuracy more than anything else.
So the to answer that kind of, you can, the amplitude is 2, right? And in a regular graph.
In a regular tangent graph, if I had a regular tangent graph, it would actually just be, it would kind of flatten out a little bit here. It'd kind of be flattening here, and it'd be a little bit more like that. That would be what the regular tangent would look like. Yeah. It just means it grows. The 2 in front means it grows up twice as fast. If I have a fraction in front, instead of my amplitude doing this, what it does, it just kind of slows down how fast it grows. Kind of like a stretch in a parabola. Remember when you're doing a parabola, when you put a bigger number in front, what does it do? It just means it shoots up faster. It doesn't change where the vertex was, it just made it grow faster. Same thing going here. It doesn't change the important points, it just makes them grow faster.
What if you had a negative in front of the 2?
If you had a negative in front, all that would do is just flip it over. So instead of going up, it would be like the cotangent going down. But my zeros would be tangent zeros, not cotangent zeros. Okay? So if I flipped it, if I had a negative in front, it would just be going down instead of going up. Okay? Question. Okay, cotangent. So the 3 in the front just means that it goes. Do I have a vertical shift? No. Do I have a phase shift? Okay. No, you do not want a phase shift with these. I do, however, have a period shift. The period is normally pi. The period on this one would be pi over 2. Okay. So what do I want to do? I want to figure out where I have zeros and asymptotes. I want to figure out zeros and asymptotes. And my zeros happen where the cosine of x is equal to 0. Or actually, in this case, the cosine of 2x. Cosine of 2x is equal to 0. So that's what I want to do, is figure out where's my cosine of 2x is equal to 0. And if I find the zeros, then my asymptotes are halfway between. Okay. So where's the cosine normally 0? Pi over 2, 3 pi over 2, right? At the odd pi over 2. What's going to do that? What number is going to do that instead of pi over 2 now? What number of x, what number do I multiply by 2 to get to that? Pi over 4. Double the denominator. If I have 2 in front, I double the denominator, find those places. So at pi over 4, if I plug in pi over 4, I get pi over 2. If I plug in 3 pi over 4, I get pi over 2. If I plug in 5 pi over 4, I get pi over 2. So every odd pi over 4. Because if I put in, any odd pi over 4, we'll shift it over to pi over 2. Okay. So I have to get my zeros from that. So I'm going to make this pi over 4 here. I have a 0. I have a 0 at 3 pi over 4. I have a 0 at 5 pi over 4. If I work my way backwards, I have one at negative pi over 4. I have another one here at negative 3 pi over 4. And another 0 at negative 5 pi over 4. Those are where my zeros are. Where are my asymptotes? All the pi over 2s, which are halfway between. All the odd pi over 4s are all my even pi over 4s, which are pi over 2s. Halfway between. So it's a narrower graph. And I actually have at the ends as well. So this is a cotangent, so it does the disco thing the other way. It's going down instead of going up. Where do these stairs go? They go down. Cotangent decreases, so I just get... Woohoo! Okie dokie, question. Find the zeros, find the zeros, asymptotes are halfway in between. Really, that's the easiest way to graph now. Questions? So we can move on. Okay. Once again, what is the cosecant? 1 over the sine. The cosecant is 1 over the sine. So here's what I want you to do. Sketch in the graph of the sine, 2 sine of pi x. This will be good practice for your quiz coming up. Sketch the graph of 2 sine of pi x. And then use that to find the cosecant. Okay, so my amplitude is 2. My period is 2, because you take it, divide it by the W in front, so my period is 2. So let's do this. So 1, 2, 3, 4. There's a 2 there. Here's a 1. There's a -1. Here's a -2. So the sign is 0 here, climbs up, comes back down to 0, goes down, comes back up. So it goes 0, 2, 0, -2, 0. Same thing going in the opposite direction, -2, 0. Oops, I screwed up on this. My distance there, that should. And then 2, 2. And then there's a 0 here at -2. And so your sign looks like this. And I've got 2 periods on the sign. Now, what does that mean for my yes? If you want to keep going, you can. Honestly, this will be enough for what we're doing in here. Now, here's the important thing is, where are my asymptotes at? Wherever the sign is 0, that's where I have an asymptote. You do need to know where your asymptotes are, because that gives you your boundaries. And you need to know where the tops and bottoms are, because that gives you the bottoms and tops. So let's see, go like this, like that, like that, and like that. Here you go. Graph the sine to get the cosecant, which means how are you going to get the secant?
Okay.
Graph the cosine to get the secant. Actually, you're going to graph the -3 cosine of x. So graph that and use that to graph your secant. That's the easiest way to do it. That is by far and away the easiest way to do it. And once again, practice for your test. Or quiz, I should say.
We should take the quiz one day.
Let's not say we did. Hey, it's completely optional. If you don't want to take it, that's fine. I can give you 0.
Yeah, just actually my parents don't like that. You won't need it. You won't need it. Do that. I really will not be here. This is so bad.
How many of you did not catch the negative in front? And thus started up high instead of starting down low.
I would never do that.
Got to pay attention to that. So our asymptotes are at the pi over 2s. And then if you really wanted to do the other parts, you could do the other parts as well. Okay. Beep, 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 beep. That's all, folks.
Bro, clean up.